All right, today we are going to talk about section 13.4, which is the cross product. So we're going to compute the cross product, find uh, vectors orthogonal to two other vectors, and we're going to find the area of triangles and parallelograms given vertices as coordinates. So let's take a look at the cross product. So last time we did the dot product, which is right here. So we've got two vectors, a dot b, and this is a scalar. And so this is sort of one multiplication that we can do with vectors. Another is the cross product. So what's going to be nice about the cross product of two vectors is that the answer is going to be another vector. So what's also interesting about this is that this vector in particular is perpendicular to both A and B. So we're going to get an answer that gives us a vector that's perpendicular to both of the vectors that we started with. So down here I've got a link to a applet that if you're looking at the PDF of these notes, that is a live link, so you can press that or we can take a look at it here. So here's the applet. I can't use it as nicely as I would like on my iPad as I can on my PC, but the two vectors that we're finding the cross product of are the blue and the green vectors, so the ones that are making that parallelogram down there in the XY plane, and their cross product is that red vector that's pointing up into the air. And so you can move these around. So I can do at least this part on my iPad, but if you look at the applet, you can click on the tails of, oh, no, it's not quite doing it. You can click on the tails of the green and the blue vector and move those around and see what happens to the cross product. So that's kind of a nice one to kind of take a look at visually what's happening. Go back to our notes here. So another way to think about the cross product is even just to look at our little unit vectors. So we've got I here, which remember is that unit vector that is 1, 0, 0. And if we have j here, and it is 0, 1, 0, if we do the cross product of I and j in that order, we get k. But something that's going to be interesting about the cross product is that the order that we do the cross product, which vector comes first, that's going to make a difference. And we'll see why in a little bit when we start looking at the computation, because there's some subtraction involved. And so then that's going to make a difference of what's happening when we do the cross product. And so we get that our vector k, our little unit vector, and that should make sense, at least in terms of that idea of it's perpendicular to both I and j, and to be perpendicular to both I and j, it's got to either go straight up from them or straight down from them. And the interesting thing that we'll see, which will make sense when we do a little bit more here, is that if we do switch that cross product, we get the opposite of what we got in the original direction. So if we did j crossed with I, we get negative k. So it's something that's interesting that we're going to have to pay attention to, and hopefully when we start seeing how we actually compute these, this will make a little more sense. And there is a nice quick way that we'll talk about on the next slide about how you can figure out what direction this cross product vector is going to point. All right, so given two non-zero vectors, u and v, both are in 3 space. So you have to be in 3 space to do the cross product. You actually can't do the cross product in 2 space. And again, we'll probably see why here in a second, but the ending reason is essentially is because we need a 3 by 3 matrix to do this, and we can't get that with vectors in 2 space. So we're going to just do vectors in 3 space, and the cross product is u cross x, and that's a vector, and its magnitude. So notice that this looks really similar to what we got from the dot product, but the difference is with the dot product, it was the actual dot product sitting here. This is, remember, this is magnitude of that cross product. So the magnitude of the cross product is equal to the magnitude of each of the vectors multiplied and then the sine of the angle that's between them. So very interesting. So again, these things are proved in your textbook if you want to see it proved, but it's not something we want to, spend time here working on. So I said just a second ago that we can figure out how that direction is going to go and what that's going to look like. And you can use something called the right hand rule for direction. And there's a lot of videos online too that if me talking this over without you being able to see my hand, and we can also talk about this in class, that that can help you visualize how this works. So if we have two vectors here, say we have our A and our B, and we want to do A cross B. Okay, that's what we want to do. And so the thought is that we're going from A to B. So I just put that arrow there not to necessarily talk about the angle, but to talk about, where we're starting and where we're going. We're going from A to B in terms of the cross product. So how you can find out that direction is if you put your right hand on that first vector. So in this case, that's A. So if we put it on our first vector and then curl your fingers toward the second vector, which in this case is B. So if you have this on a tablet or a piece of paper, if you put your right hand on vector A and then curl your fingers towards B, and where your thumb is pointing, in this case it's pointing up, it's pointing out of the paper or out of my tablet, that tells me that our vector, when we do the cross product, that's going to point out of the screen. If we flip it around and do not A, do B cross A, so if we go the other way, if I put my right hand on B just as it's sitting right now, if I curl my hand, I'd have to go the long way around to get to A, and we always go the short way around to get to the other vector. We always do the acute angle, or not the acute angle, the angle that's less than 180. Sorry about that. But if I flip my right hand over so that my thumb is pointing down now, then I can curl my fingers towards A with that angle that's less than 180. And my thumb is pointing now down into the screen. So this one goes into the screen. And it's the same vector, but it's just going the opposite direction. So again, we'll see why that happens with the arithmetic that we do for this, but that's a quick way to tell whether it's pointing, up and out of the screen or down and into the screen. Okay. So let's take a look at how we do actually compute these cross products. So we're going to start with reviewing something that you might have learned some point in high school algebra, possibly, if you did some things with matrices. If you didn't, don't worry too much about this. This is not a super hard concept to get. So I have faith that you guys can get this. So we're going to look at the determinant of a 2x2 matrix. So given A, which is A, B, C, D, if it's been a while since you've looked at a matrix, here's what a matrix is. It's basically a spreadsheet of numbers. It's got two columns, two rows, and when we talk about things like 14 here, that's sitting in row 2, column 1. This is a matrix with some numbers in it down here. Okay, so we've got A, B, C, and D. Those are the numbers in our matrix, and the determinant of A, which when we write that in another way, we put absolute value bars around A. So now this is probably, I think, the third use of these kinds of absolute value bars, because we use these for magnitude, we use them for absolute value, and now we're using them for determinants. And normally when we might write a matrix, we put these sort of square brackets on it. And here with the determinant, we can put those numbers in that determinant with those absolute value brackets. And the determinant is a number, and it is literally just A times D minus C times B. So those diagonal elements multiplied together and subtracted. So down here in our quick example, the determinant of A, which would be -2, 3, 14, -12. I blame my daughter for these numbers. I asked her to give me some numbers, and of course she started giving me like things in the teens. So she's making us do some arithmetic here. But again, it's going to be that A times D and that B times C. I apologize if you can hear the mini blinds in my bedroom rattling around. One of my cats is in here playing, as always. um, and when we do our arithmetic, we get negative 18. Okay, so the determinant is a number. So how we're going to use this to help us get the cross product is here. So we've got our two vectors in 3 dimensions, and we're going to set up a matrix. So the first row of this matrix is just going to be our labels um, for those x, y, and z components, I, j, and k. And then in our matrix, the second row is going to be that vector u, so the first vector in our cross product. And then that last row is going to be that second vector in our cross product. Okay, so how we get the determinant of a big 3 by 3 matrix is that we split this up into little 2 by 2 ones. So what we're going to do for the first one for I is you cross out the first row and the first column, and that little matrix that you have left, U2, V2, U3, V3, we're going to multiply that by our I component. So the determinant that we get from that little matrix without the top row and without the first column, that's going to be our coefficient for our I component. And then we're going to erase this because then the coefficient for the J component is going to be, we're going to get that matrix from crossing out, again, that first row and crossing out the J column. And we're going to subtract this one. And we're going to have all of the components except for the actual J components. We get rid of the components that are actually the second components. We use the first and the third, the determinant of those, to get that coefficient for J. And then lastly, for the coefficient for the K component, we are going to cross out that first row and cross out that third column. And here we are going to add the determinant of U1, oops, V1, U2, V2, and that's going to be our coefficient for the K component. So there's another pattern here that we want to kind of pay attention to, that this first one, this actually does, we don't write it, but it does have a plus out from in front of here. And then the second one is negative, and then the third one is plus. And it's kind of the same pattern. It is not even kind of the same pattern. It's the same pattern here. This first term is positive. The second one is negative. And if you had a bigger matrix that was maybe a 4 by 4 or a 5 by 5, when you're doing this, that pattern continues. It goes plus, minus, plus, minus, plus, minus, plus, minus for as many as you have to break them down. But we don't need to worry about that. We're just looking at this 3 by 3. They're always going to be 3 by 3. It's always going to break down this way. And so, I mean, this does end up being U2 times V3 minus V2 times U3, and that's going to be our coefficient for I, and then minus U1 V3 minus V1 U3 J, and that's our coefficient for our J component, and then plus U1 V2 minus V1 U2, and that's our coefficient for our K component. So this is going to give us our new vector that's perpendicular to those original two. Now, I do not think it's a good idea to memorize this at all. What I think it's good to memorize is this idea of we cross out that first column, or that first row always, and then the column that we're finding the coefficient for, and that gives us that little matrix. So if we remember that, and then also that plus minus plus pattern, that's all we have to remember. Remembering where exactly everything goes and memorizing this kind of thing, oof, that's a nightmare. So let's look at this with some numbers. Okay, so our cross product, and I should have said the order, but we'll do U cross V. So we set up our determinant. So I, J, K, remember things go in alphabetical order. And then we have that first vector first, the second vector second. And then to get what our coefficient of the I component is, we are going to use the determinant of the matrix that's left after we cross out that ijk row and the first column. And this is our coefficient of our I component. And then always minus for the j component. Let's see. I don't know if I can, oops, there we go, good. And then now for the j component, we're going to always cross out that first row, and now we're going to cross out the j column. And then the numbers that are left, that's going to give us our little 2 by 2 determinant to get the coefficient of j, and then plus k. K again always gets a plus, and we'll cross out again that first row and then the k column, and the numbers that are left give us our coefficients, our determinant, so that we can make our coefficients for the k term. So I'm going to not do all of the arithmetic on this. I'm going to let you do the arithmetic of the determinants. Make sure that you can get the same thing that I got. I'm trying to save us a little time on the video, so this isn't, you know, a 40-minute long video here. So do these little determinants. Again, it is those diagonal elements. That first diagonal gets a positive, second diagonal we subtract. All right, one other thing that we want to talk about with this, so you're going to be finding some cross products, and again, the other thing that's cool is that this is orthogonal to both u and v. That cross product that we get is always going to be orthogonal to both of those vectors that we started with. All right, one of the applications of the cross product is that you can get an area of a parallelogram or a triangle. So what's kind of interesting, and if you look back at that applet that we had, there's a little parallelogram right there that we made with the blue and the green vector. So one of the ways that we can look at a parallelogram, come on, come back. Oh, what page is it on? There we go. Wasn't on the right page. Is that we can take one of these vertices here and say, okay, this is going to be a vector, and we'll call it vector A, and then this side's going to be a vector, vector B. And we can view that we made this parallelogram by taking those two vectors and then, you know, adding the other two sides that are, you know, equivalent or parallel vectors there. So we could talk about the angle between our two vectors here. And if we remember, you know, finding the area of a parallelogram, maybe it's been a little while, it is the base times the height. It's the same as for a rectangle. So the base, that's not too bad. The base of this is the length of that vector b. So it's the magnitude of b. The height of this, though, the height that we're talking about is from that top vertex here down, dropping down a perpendicular. Here is the height. So we want to know what that height is. How long is that? Well, that angle there, theta, that's the angle between our two vectors. And if we think about our trigonometry, sine of theta is the opposite side over our hypotenuse. And in that little triangle that we have there, this one here, the hypotenuse, the length of that is the length of vector A. So this we can solve for our height. So we can multiply both sides by that magnitude, sine of theta, and that's equal to our height. And then we can put that right here. That is the magnitude of A times the sine of theta. Now, if we go back to slide 3 here, look at this. The magnitude of u times the magnitude of v is equal to the sine of theta, or times the sine of theta is equal to the magnitude of our cross product. So the area of this parallelogram is equal to the magnitude of the cross product of those two vectors. Now, what's nice about this is it actually doesn't matter whether you put A or B first, because whether that vector, that cross product vector points up or points down, out of the screen or into the screen, when we find the magnitude, we're squaring everything. So the direction that it goes doesn't matter because it's going to be the same length whether it's pointing up or pointing down. So you could do A cross B or B cross A. So very cool. The magnitude of the cross product of those two vectors is the area of that parallelogram. And then from this parallelogram, I drew a triangle because we can extend this really quickly if we've got vectors A and B. And remember, with a triangle, the area is equal to 1/2 the base times the height. Well, we could go through the exact same process, and this is just going to be 1/2 of the magnitude of the cross product. So very cool. We'll do some more examples of this, of course, in class. And let me know in the quiz if you guys have any questions.